So we will continue talking about inductance, and we will consider two circuits when inductance is connected to a resistance or to a capacitance, and maybe to both of them, resistance and capacitance, depending on how much time we have. And conceptually, it shouldn't be hard. So, but we will use some knowledge from previous material. So let's start with RL circuits. RL circuits, meaning that I connect resistance and inductance and maybe a battery in an electrical circuit. So we can also have a process of charging or discharging, but I put in quotes charging or discharging, meaning that we will try to create current, and the current will die if you discharge this inductance through a resistance. So how can possible charging process look? So let's say you have a battery, EMF, you have a switch which you can close, you have a resistance, R, and you have inductance. L. So let's say at time equals 0, you close the switch. So before time equals 0, the switch was open. That would be something I would call charging. Charging by analogy with RC circuits. So what does it mean charging for me? That means at time equals 0, I don't have any current. When I just close the switch, so I'm going to put it to this position 1. Then current cannot really start immediately to be, let's say, EMF over resistance value because of the inductance. Inductance will resist. Inductance is not going to allow you to jump for current. So if you're talking about current as a function of time, current as a function of time, you cannot really jump from 0 to any finite value, because in this case the derivatives over time will be too large. And if you have this too fast change in the current, then the back EMF will be huge. Yeah, remember, back EMF will resist the change in the current. So inductance is not going to let you do this, because the derivatives will be infinite and the back EMF will be very large. So if we understand this, then we can say that the current should, instead of this picture, the current should build up slowly. So the more realistic picture would be, then when at time equals 0, you close the switch, the current will start to build up, and only after a certain time, actually after infinity, but there will be a time constant. After some time, the current will rise significantly. What can we say if you wait long enough? So if I wait long enough, so initially my current is 0. Yeah? If I wait long enough, what would be the current? What would be your guess?
Can't hear you, Lenin.
Sorry?
Isn't current max?
Yeah, it will be maximum value, and what will be this value? When you wait long enough, the current will go and become a constant current, and for this case, the inductance is just a wire with no resistance. And when current is constant, there is no back EMF in the inductance. So then just you can replace inductance with a piece of wire. In this case, the current will be the maximum value, yes. But what is this maximum value? EMF over, let me replace EMF with V, the voltage. It will be the voltage over resistance, yes? That would be a typical charging process, and the equation for this charging process will be similar to RC circuits. When we were talking about RC circuits, we were talking about charge, how you build up charge. And the function was the same. So the charge was 0, and then the charge was building up, and there was a time constant RC, which will give us the typical time of charging. So now we can speak about charging in this same way. So we can pick a loop. We can write a loop rule. I'm gonna go clockwise, starting from the battery, the voltage V. Then you have a resistance. Let's say you have a current multiplied by resistance. And then you have a drop of potential across the inductance. Let's say the direction of the current and direction of the loop is the same, so I'm going to put negative inductance di over dt, and it should be 0 because this is a loop rule. Let me remind you what we had for RC. For RC, it was the same. It was the battery, then minus current multiplied by resistance, but the current is the charge over time multiplied by resistance, and then minus the drop of potential across the capacitor. So it's a Q over C. Can you see that these guys are similar to each other? You have a function and you have a derivatives of this function over time. You have a function and you have derivatives over this function over time, yeah? And you have a term which is constant. And we have the same initial condition. Initially charge was 0 for RC, and initial current was 0 for RL circuits. So then the solution will be the same. I don't know if you can see this, but this is absolutely the same equation. Maybe I have to regroup these terms. Let me regroup this a little bit so to make it more obvious. I'm gonna just put them in different order. So instead of current, you have charge. And instead of derivatives of current over time, you have dq over dt. And the coefficient is r. So we can take the solution for RC circuits and we can replace the parameters. So for example, I should take capacitance and replace this with 1 over resistance, just if I want to compare the coefficient. And I should take resistance and I should change it with inductance. So the substitution will look like this. Let's take resistance in RC circuits and substitute this with inductance. You see what I'm doing? I'm trying to look at the coefficients here. So this is how this transforms. Of course, I have to replace charge with the current now. I have to replace resistance with inductance, and a little bit less trivial, I have to replace coefficient 1 over C with resistance. So this means I have to replace capacitance with 1 over R. So this would be the substitution for me. So I can take the solution which I already know, and I'm gonna do this substitution like this. And of course, V does not change. V I replace with V, so I don't, because the term is the same. And this is the beauty of physics, because if you know solution for RC circuits, you can just use this solution to solve RL circuits. You don't really have to do any work, extra work. But you have to be very careful to prove that this is the same equation and this is the same initial condition. So then we can just write the solution. So instead of Q equals Q max 1 minus exponent T over tau, we can write solution for RL circuits. And in this solution, what was Q max? It was capacitance multiplied by the voltage, and the tau was RC. So now I max. I have to do the substitution. The voltage will stay, and capacitance I replace with 1 over R, if you remember from the previous slide. This is not a surprise. We know that the maximum current after a long time should be V over R. Yeah. What about time constant? Time constant was RC. I replace resistance with inductance, and I replace capacitance with 1 over R. This would be the new time constant. Maximum current. Basically, that's it. We just solved the problem. Honestly, we don't even need to do any examples about this, because with this substitution, it's just equivalent to RC circuits. You can do the same. The only probably difference between capacitance and inductance, and after long time, the current through the capacitor is 0, but you have certain charge. And inductance, after a long time, inductance will change into a piece of wire because current will be constant. The inductance is not a piece of wire only if current is changing and you have back EMF. But if you wait long enough and all these transitional processes will end, then it will be just a piece of wire because all your currents will be constant. And we can do also relatively fast discharging. So by discharging, I mean that you have current at some initial time, and the current will go through the resistance like this. And eventually current will die because you're going to lose energy into resistance. And with time, gradually, whatever you have will dissipate. So you can write a loop rule, and the loop rule will look something like L di over dt would be equal minus I R. And of course, the solution would be similar. If you have some initial current at time equals 0, then the current as a function of time would be some initial current and this exponential decay. And of course, tau is the same. Oh, I put resistance in wrong place because I confuse it with RC. So it's going to be inductance over resistance. So then if you remember for the charge, for discharging proteins, we had the same equation, yeah? But I would rather want to show you some analogy with mechanics. This analogy with mechanics is always fascinating to me. I don't know why, but if I try to translate this to mechanics, then I would say you have some inertia, the rate at which you change velocity. So current will play role of a velocity, inductance is inertia, equals minus some coefficient, and then velocity. I don't know if you remember this equation or not, but it would be just a friction force. And this is a mass times acceleration, yeah? It could be air drag force, and beta will be the friction coefficient. So you have a net force, only the friction force. And the particle will slow down because of this friction force. So if I want to draw a graph, what's going to happen to velocity as a function of time? It will exponentially slow down. So you have some initial velocity v naught, and then with time, because of the friction, the velocity will decrease exponentially. But this is the same equation for inductance and current. Look at it, it is the same. Yes, absolutely. So, and the solution is the same. It's exponential decay. So interesting that resistance in this case, the resistance plays the role of a friction coefficient. And also, if you talk about energy conservation, when particle is slowing down due to air friction, air drag force, you lost kinetic energy into air, basically. You make air move around. You lost it because of the friction force. So in this case, inductance also has some energy, and we're gonna lose this energy because of resistance. So resistance will take this energy and change it into heat, basically. It's almost the same like you have air drag force, which will change your kinetic energy into heat. So this is a full analogy between these two equations. That's nice. We can solve one example because I don't really want to stay too long on this. I would just refer to RC circuits, and I would refer to this kind of analogy when you can translate one set of equations or situation to another. This one. This is a good analogy or good set of substitutions from RC to RL. Questions? Probably we need just one example. It depends if you want to go really to complicated examples or not. Let's start with something simple. So I have a battery. I have a switch. Maybe I have a resistance. Let me put switch in different place because I want to switch between different situations like this. This would be the switch, one more resistance, inductance, let's say another resistance here. V, R1, R2, R3, L, and you have a couple of positions, 1 and 2. So let's say I'm gonna close the switch to position 2 for a long time. Then at time equals 0, I close it to position 1, wait long enough, and then I switch it back to position 2. And I would want to describe the current through the inductance as a function of time. So R1, let's say 1 ohm, R2, let's say 3 ohm, R3, maybe 5. The battery is 24 volts and inductance is, let's say 5 millihenry. So I'm gonna close this to position 2 for a long time. Switch is at position 2 for a long time. So now at time equals 0, I'm gonna put it to position 1. I'm gonna switch it to position 2 again. Let's put position 1. So then we're gonna start charging process, yeah? And because the switch was at position 2 for a long time, the current was already 0. The current will die. How would you describe current as a function of time for this after time equals 0? At position 1, it will be charging or discharge process.
Isn't position 1 charging and 2 discharging?
Yeah, position 1 will be charging, so we will try to build up the current. And if I then change it to position 2, it will start to discharge. So the current will start to die through the resistors. Okay, so then in this case, I can write the solution for the charging process. Assuming that the initial current was 0, the current would be I max multiplied by 1 minus exponent minus t over tau. That's it. We solved the problem, yeah? At least for the first part. And what is the I max in this case? Remember, that was a maximum current.
V over R?
V over R. I have R1, R2, R3.
R1?
No,
Oh, no.
but it's close.
R1 plus R2.
R1 plus R2. If you connect it to position 1, R1 and R2 will be connected in series. Yeah. So V over R1 plus R2. And what would be the tau? The time constant. Let's call this tau 1. What equation would you use to find the time constant?
Is it the L times 1 over R?
L over R.
L over R.
Which R?
R1 plus R2? Yeah.
Yeah. So we can find them. So I max would be 24 volt over 1 plus 2 over 4 ohm. So I guess it's going to be 6 ampere. And the typical time constant for this charging process would be inductance, which is 5 millihenry over 4 ohm. 5 over 4, yeah. 1.125 milliseconds, I guess. 1.25 millisecond. So it will take pretty fast, actually almost no time, yeah, to reach the maximum current. We are talking about 1 millisecond, so it's kind of immediate. Let's go back to the picture I drew before here. The difference between very sharp change and a slow change. So inductance will play a significant role in this. If my inductance is small, then the time constant is small. So then going to be a very short process. So this may look like this. If inductance is 0, it will be very sharp. When you just close the switch, if there is no inductance, the current will jump up almost no time. But once you have non-zero inductance, you have a non-zero time constant, so it's going to take some time. Tau, to build up this current. Well, in the example which we work with is the inductance is millihenry, so we are talking about milliseconds. I don't know if it's a large time or small time, it depends to what you compare this time. But what is interesting that the time constant is proportional to the inductance. The greater this value, the longer it will take to build up the current because you will have more resistance from the inductance. It makes perfect sense, yeah? So then we can write the solution there. The current as a function of time would be 6 ampere multiplied 1 minus exponent minus time over basically 1.25, 1.25 milliseconds, something like this. So if I need to find time current at certain time, I probably can plug the time. So let's say then at time equal 2.5 seconds. Let's wait 2 time constants, 2.5 seconds. At time equal 2.5 seconds, I'm gonna switch it back to position 2. And I'm gonna initiate kind of discharging process after this. And I can ask the same question. What will be the current as a function of time after you change the position? The switch is put to position 2 back. And then let's find the current as a function of time. Because now it's a discharging process, yeah? So the discharging process will follow this nice equation. I note this is the initial current that was at the moment of switching. And then minus t over tau, the only difference is I would say the tau time should be counted from the moment of the switch. So, or maybe I should say something like this. This is a different time, I guess. This is a time at the moment of when you start discharging. If you want time from the very beginning, then probably you should put t minus 2.5 milliseconds to be more accurate. I would not bother shifting time. I would probably just say that this time is calculates from the moment of the switch. So and then I'm going to just keep this way. I would more like to know what is I naught in this case and what is tau in this case. let's look back at this diagram. What will be the time constant when you switch it to position 2? The time constant.
L over R, R3.
L over R, accepted.
R3.
What kind of resistance?
Oh, is it R2 and R3?
You mean plus?
Yeah.
Yeah, they connected in series again. R2 plus R3 would be the equivalent resistance, and inductance will, let's call this discharge, through the R3 plus R2. And the initial current, the current had some value at this moment of switching. This value will stay because you cannot change it immediately. Inductance does not let you to change it immediately. Whatever current was when the switch was at position 1, that would be the initial current for the second part. So we can find it from the previous part, but we can find the time constant. It's inductance over what? R2 plus R3, yeah? So I can find this without problem, I guess, 5 milli Henry. And what was my R2, R3? It was 3 and 5, so 8. 3 and 5, 8 ohm. Hmm, 5 over 8. It's a 0. What is this? 5 over 8. So we're talking about milliseconds, yeah.
65. Oh, milliseconds. Hold on.
1 over 6 to 5, no? It should be, yeah? Or not?
Yeah.
Yeah, that's right.
I hope so, yeah. Mm-hmm. So it's a new time constant. How would you find the initial current then? The current that was right before you change the switch. We can use the previous formula for this. The current was building up, and when time was 2.5 milliseconds, we changed the switch. So at this moment, there was some current, and we have to use this current as the initial value for the second part. Okay, sounds good to me. What was it? 6 ampere, yeah? There was 24 over 4, yeah, 6 ampere. Okay, I believe I need your help on this because this will be exponent in -2, and I need some help in calculating this. It should be very close to, I don't remember, 83% from this 6 ampere. So it could be 5 ampere, around 5 ampere.
Yeah,
5.2.
5.2?
Yeah.
Okay, so then we can write the solution. Let's put here T prime. The time calculated from the moment of the switch, when the switch was changed, not the dead time, that was just a global time. I can just draw maybe the main diagram, what happened with time when you have both of these processes. So you have the 6 ampere value, 6 ampere. At time equals 0, you start charging, so your current is increasing. And when you reach this time, 2.5 milliseconds, you reach value 4.2, 5.2, sorry, yeah? Which is not 6, but it's close enough to 6 ampere. At this moment, you not continue charging process. You change the position of the switch and you start discharging. So T prime would be calculated from this point, from 2.5 milliseconds and further. So this is the first part on my left, this is the charging, and the second part is discharging, starting from this 5.2 ampere value. Well, that's good. I believe it's pretty much straightforward and simple example. It's absolutely the same as if I put capacitor here, and I'm going to ask you about the charge, not about the current. You will just change a little bit how you calculate maximum charge and how you calculate the time constants. That's it, yeah? The rest would be absolutely the same. Question? It's all good? You see the power of knowledge or science. We know, we went through these RC circuits, we know the solution pretty well. And then we use this analogy to solve another problem. Apparently, inductance is something different from capacitance, very different. But the equations, they look the same, which is nice. It helps me to solve the problem without any efforts. This is a strength, it's a certain power of me and you now. Questions? Also, this analogy, I like it too. This is nice. So it tells you that inductance is some kind of inertia and resistance is some kind of friction coefficient. Okay, that's it, yeah? Yeah, I don't believe we need more examples unless you ask me. We can rather talk about LC circuits. And maybe I can also mention about RLC if I have all of them connected. So LC circuits, they have very interesting analogy too. And we're gonna write the solution for these LC circuits without solving them again. So let's say you have a capacitor with some initial charge. Then you have the switch and inductance. So at time equals 0, I'm not going to have any current, but I'm going to have charge. And then at time equals 0, we're going to close the switch. It would be interesting to see what can happen in this system. Well, if this is just a piece of wire without resistance, then the capacitor will start to discharge. And the time of constant for this discharging would be very small, because time of constant is RC, and there is no resistance, yes? And what we're gonna see, the capacitor will just discharge in no time. But when you have inductance, the life will be more interesting because inductance is not gonna let you to have a strong current. It will gonna let you to have current, maybe increasing gradually, but not immediately and not very fast. So there would be a transition process again. Is it going to be exponential or not exponential like for RL circuits? We don't know yet. Also, when you have a current through the inductance, and even if capacitor is already discharged, the current cannot die right away because it has inertia, inductance, and the current will continue dying gradually because inductance will resist to this process. So then let's solve this. Let's find the loop rule for this, and let's see how we can do this. So if I go clockwise, the drop of potential across the capacitor would be the charge at this moment over the capacitance. This is a drop of potential across the capacitor. Then because of this you have current going this way, and my direction of the loop and direction of the current is the same. So I have to write something like this. And it should be 0 because I don't have anything else in the circuit. So later maybe I will put resistance also. So then I will have a resistance on this. So unfortunately this equation is not very easy to solve. I have to relate the charge and the current. And you probably, with a big chance you can make a mistake. What would be the relation between charge on the capacitor and the current? What could be your guess? How current is related to the charge? Normally current is the rate at which charge changes, yes? Plus or minus?
Minus.
Minus. This is very good. I did not have hope actually. I thought you will make a mistake. But this current is removing charge from the capacitor. This is why it's minus. It's absolutely nice that you can say this. It's like a discharging process for a capacitor. For discharging process for a capacitor, we also had minus. Okay, this is good. Plus you have these initial conditions. Now we can solve this, and to solve this I'm going to rewrite this like this. L di over dt equals 1 over CQ. That's one line. Then I'm going to plug the current as a derivative from the charge over time. So there would be second derivatives. I'm going to have negative sign, of course, so let's keep this negative sign. And you will see right now why negative sign is that important. And finally, my equation will look like this. I'm going to cancel this negative sign. And this is one of the most beautiful equations, and I'm sure you know this equation, and you know the solution of this equation. And not only the solution, you know everything, literally. Let me write another equation. M is second derivative from the position over time equals some constant multiplied by the position. let's try to look and let's try to see if there is an analogy. Between these two equations. So you have a variable x, q. This is the rate, so it's the rate of change. So this is acceleration, yeah? Second derivatives over time. This coefficient will play role of inertia. The mass times acceleration. Inertia times of acceleration. This is acceleration of the rate of the change of the charge. So it's a rate of the so it's acceleration, yeah? But not for motion. It's how fast current is changing. Then 1 over c coefficient will play role of, that was spin constant. So then this system describes me oscillation of mass m attached to the spring of some spin constant k. So we know exactly what kind of solution is this. These are harmonic oscillations, yes? For harmonic oscillations, we know everything, literally. We know kinetic energy, we know potential energy. When we can do these phase space diagrams, if you want to be fancy about simple harmonic motion. We know how to find x as a function of time, how to find v as a function of time. We know that there is a frequency of oscillations and period. We know full solution in all the details. Then we can do this for the LC circuits in practically no time. What I had to do is just to write the loop rule and then to see that my final equation, the result, is the same as something I already know. So the result of this would be simple harmonic motion. And we have a lot of experience from the previous semester. Yeah? So then what would be the substitution for me? So I have to replace position x with a charge and velocity with the derivatives over time with the current. My current is negative. This is just about direction. So I would be careful on this. It depends what direction of the current you want to pick. Okay. Then parameter m, traditionally I replace with inductance. Then parameter k, I replace with 1 over c. For simple harmonic motion, you have omega. Omega was square root of k over m. What will be omega in this case? If you do all the substitution, what would be the formula? Yeah.
Square root of L over C.
1 over LC. Yeah? Because m you're going to replace with the inductance and k with 1 over c. Beautiful. So then you can find the period and the frequency. So the frequency is omega over 2 pi. And the period is 1 over frequency. Wait a second, is it correct? Well, it seems so, yeah, it's 1 over frequency, omega over 2 pi. Yeah, it should be like this, yeah. Again, we see that the typical time for this LC circuits will be proportional to the inductance. It will be proportional to square root of inductance. This is a little bit non-trivial. Square root of inductance, not inductance, not linear dependence. But it's okay. So then if you write a solution, the solution usually looks like this. Amplitude multiplied by cos omega t plus phase shift. That was solution for simple harmonic motion. So now we can say q as a function of time will be equal some amplitude q max multiplied by what? By cos nu omega, whatever omega is, then the current as a function of time, it's a negative. Let's keep this negative sign, even if this is just a direction, but still. So then derivatives from the cos would be minus sign, but I have negative sign. That's going to be omega q max sine. So we can conclude that q max and I max are related to each other. Can I say something like q max over square root of LC? In terms of graphs, there's going to be oscillating functions with some period and some frequency of oscillations. So let's put phase shift phi naught to 0 just for simplicity. Then my charge would be a cos function. So it's a q. And my current would be the sine function. The only that is negative sign, which is kind of non-trivial. So sine. Then what can we say? When you have a maximum charge, you have no current at this moment. Maximum charge is like maximum deviation for a simple harmonic motion. When you have maximum deviation and you let it go, at this moment, at maximum deviation, you don't have velocity. You don't have current. Yeah? But then the capacitor will start to discharge. And you have current increasing, 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 increasing. When you have no charge on the capacitor, you have maximum current through the inductance. At this moment, the capacitor is not charged. But current cannot stop because it has inertia. It's like a simple harmonic motion goes through the equilibrium. When a particle goes through the equilibrium, you don't have force because you don't have deviation. You're at the equilibrium. But you have velocity and you have inertia. Then the particle will continue to move and the spring will start to compress. So this means you start to have negative charge. So you're gonna start charging capacitor. And you can charge it to maximum charge. At this point, the current will die. And then you start discharging process again, but with different polarity. Then the capacitor will start to discharge and the current will start to grow, but that would be current in different direction. It is very close to, if you look at the oscillation of this guy on the pendulum, not pendulum, but this, the mass spring system, how it oscillates left, right, left, right, left, right, and LC circuits. So it's gonna be discharging in one way and then other way. We're going one way, then we're gonna charge other polarity, and then other discharging, discharging, charging, discharging, charging, discharging. It's gonna oscillate like this forever, because in both cases you don't have any dissipation of energy. So you need to have resistance like friction if you want to have dissipation. So this LC circuit is described in absolutely the same way as simple harmonic motion. It's always the same. And we didn't even put any force into finding this out, yeah? All what we were doing is just writing down the solution. We didn't solve it, yes, we wrote the answer. This is nice. It's even more nicer because we can look into energy conservation law in addition. So speaking about energy, mechanical energy, that was kinetic energy plus potential energy. And that was constant. So if you don't have any dissipation, that kinetic energy plus potential energy was the same, yeah? That was all time the same. So what about now? What will be the energy of the basically capacitor and inductor?
Is it Li square over 2 and then 1 over C Q square over 2?
Yeah, can you recognize this? This is energy of a capacitor.
Yeah.
And this is energy inside an inductor. So if you try to draw a phase space diagram, because Ada likes phase space diagrams, we can draw this from here. Charge and current. Then if you look at this equation, this would be an ellipse. I don't know if you can see this or not. If I divide it by the energy, it's going to be 1 equals L I square over 2E plus Q square over 2CE. You may recognize the formula for an ellipse. Yeah? Like this. So the size of this ellipse will depend on energy, of course. The greater the energy, the larger will be the ellipse. So when you have evolution in time of your particle, or in this case it's not particle, it's a charge and current in LC circuit, then they will keep moving along this ellipse because energy is the same. So they can really step out of this ellipse. So, and we can see what kind of motion it can be. Let's say you have a maximum charge, maximum deviation, and no current. So then you are here. At this moment, you have capacitor fully charged and there is no current, yeah? And then you let it go. What's gonna happen next? Well, let's say you'll go this way, you'll start to have current, positive current, and the capacitor will start to discharge. When you reach a vertical line, what's gonna happen? You have maximum current and no charge. then mean you go through the equilibrium. Then you continue to have positive currents. Oh, yeah. So then you start to have a negative charge on the capacitor, and eventually when you get a maximum possible negative charge, the capacitor, the current will stop. And then you start again discharging process, but with negative current. And you will continue to move along this ellipse over and over and over. So you know the period, how long does it take for you to complete this one cycle. So the period is 2 pi square root of LC. Yeah. You know maximum current, you know maximum charge. So you basically can completely describe the solution. In terms of kinetic and potential energy, in this case, instead of kinetic, I have energy inside the inductor or inside magnetic field. And I have energy inside the capacitor, like potential energy. It will be energy inside electric fields. So it's interesting that when you speak about energy conservation, then we actually are talking about conversion of energy between electric and magnetic fields. So you have electric field inside in the capacitor, and let's say you have magnetic field inside the inductor. So you change energy from electric to magnetic fields, and then back from magnetic to electric. When you don't have charge, then you don't have electric field. All the energy will be inside the magnetic field because at this moment you have the maximum current. But when you don't have current, when you momentarily stop current, when current is zero, you don't have energy inside this magnetic field. But at this moment, the capacitor is charged to its maximum value. So then you have the strongest field. So if you can plot this graph, so energy is a function of time. So let's say your charge is cost function and you make this cost function square, then the potential energy or energy inside electric fields will be like this. And the energy inside the magnetic field will go with a shift. So it will be sine square function. Of course, if you add kinetic energy plus potential energy, you'll get just energy. So blue one is the energy inside the electric field. So we can say, okay, I'm not going to say this, but it's like electric field square, epsilon naught, and then volume inside the capacitor. And then you have energy inside the magnetic fields. And you always change one type of energy to another type of energy. Yeah. So when it's oscillating, so basically you have oscillation, which is interesting in this circuit. And this is how energy changes. So I believe if you go from, so this is a zero, negative, zero, maximum. So this would be the period. And from maximum to maximum is a half period. Nice. And again, it came to me for free. Because I know very well simple harmonic motion. I just know everything like this from the very beginning. Isn't it nice? Let's solve one or two examples just to refresh your knowledge of simple harmonic motion. But I'm just repeating the material about simple harmonic motion that we studied previous semester. You may even remember these graphs like this, yeah, that we used. Questions maybe? That would be a non-trivial formula, which is kind of very non-trivial. How would you find the frequency of this simple harmonic motion? Because you may remember square root of k over m, that's nice. But this would be new formula. 1 over square root of L and C, which is non-trivial, I would say, but this is how it is. Interesting that 1 over capacitance plays role of spring constants. That's kind of also non-trivial. Questions? Should we do one or two examples, yeah, to make it more clear?
Actually, I do have a question, not really related to this, but kinda.
Mhm.
I was doing the cheat sheet for the exam, and there were some problems that kind of reference stuff that we learned before in mechanics. Should we put those formulas as well? Like, how can we bring a book?
No, you
A
can
book of
bring-
formulas?
No.
Because, yeah.
You can put some mechanical formulas if you want. You can use both sides of your cheat sheet. That's fine.
Okay.
Yeah. So let's do something very simple. So let's say you have a, I don't know, the capacitor which is initially charged, and then you have switch, and then you close it, and I can ask some questions about this. So time equals 0. Your charge on the capacitor is given to me. Let's say 10 microcoulomb. The current, of course, is 0 because the switch is open, and I'm going to close the switch. So let's say you have capacitance and inductance. So capacitance would be 300 microfarads. Inductance, let's say 50. Okay, let me cheat a little bit. No, not much, but just maybe a little bit. So 1200. Yeah, 1200 micro millihenry. So let's say it's a large value. So basically 1.2 Henry. Yeah, let's change it to 1.2 Henry. So at time equals 0, we close the switch. So this initial charge that was on this capacitor will start to move from positive plate to negative plate through the inductance, and the process will continue. Yeah, you have a relatively okay capacitance and large inductance. So then we can ask hundreds of questions. So write charge as a function of time, write the current as a function of time. So let's select the direction of the current the same as we used before. What is the maximum charge? What is the maximum current? What is the maximum kinetic energy or energy in the inductor? Or what is the maximum potential energy or energy on the capacitor. What is omega? What is frequency? What is period? A lot. So then maybe we can start with omega and frequency and period. As the first part. So when you close the switch, you're getting LC circuit. So you know this is gonna oscillate. It's like simple harmonic motion. So then what will be the period of these oscillations? What will be the omega and what will be the frequency? Which one you would calculate first?
Well, the period is 2 pi square root of LC.
Yeah. And I tried to adjust L and C so you can take a square root from this without calculator. Let's see. 300 microfarads, so it's going to be 300 10 to negative 6. Wait a second, this should be microfarads. Yeah, it's a capacitance, not microcoulombs. My bad. Sorry. Farads. Then I multiply it by 1.2 Henry. How much we're gonna get? Ten to minus 4. 3.6. Oh, I miscalculated. Did I?
I got 0.9 12
For everything or for square root?
for everything.
Mm,
0.119.
Under the square root, it's 360 10 to the minus 6. So
yeah, square root of 3.6. And then you have 10 to negative 4, 10 to minus 2. And I miscalculated because I forget to put 1 0. Okay, let's keep it as it is. It's my bad, so I have to pay price.
Yeah, I
for
got
this.
this thing.
Okay, what is the total period?
0.119.
119? Then what will be the omega? It's a 2 pi over period or 1 over square root of LC. So it should be close to 50, but maybe more than 50, yeah? Between 50 and 60, so 55.
It's 1 over 3.6 times 10 to the minus 2.
Well, this is omega, yeah? Oh, this is square root of LC,
Oh, right.
if I'm not mistaken.
Yeah, 52.7.
So it's the radians per second. And finally, the normal frequency. So I have to divide this 52.7 roughly by 6. So what should I get? Close to 8 or 9. 8.5 Hertz. Well, definitely not 8.5, but something close to this, yeah?
8.4.
8.4. So then we know it is gonna start oscillating. So I have initial charge 10 microcoulomb, and then it will start to discharge. When you don't have initial current and you have maximum charge, then I would say that the phase shift should be 0 for this solution. Maybe as a second part, we can write the answer for Q as a function of time and the current as a function of time. So Q is a function of time. There's going to be something like this: Q max multiplied by cos omega t plus phase shift, and I negative Q dot, it's I max sine omega t plus phase shift. So when I have initial time moment, when I just start motion, my current was 0. It tells me that the phase shift could be 0. And then my charge was maximum, and then it will start to discharge, it will start to decrease. So I'm kind of comfortable with phi naught equals 0. It will give me the right solution. And also Q max will be just my initial value, yeah? It will be just 10 microcoulomb. So I'm gonna try to satisfy what we call initial conditions. Omega. What was omega? What was the angular frequency? 52.7, yeah? How can you find the maximum charge? Imax. Oh, sorry, maximum current. Maximum charge you found.
Isn't it omega multiplied by charge max?
Yeah. Remember we had this equation. V max was omega amplitude. I don't know if you remember this or not, but we did have this before. And probably I wrote this too. If I go back to check just very quick. Yeah, here. I max is omega Q max, yeah? So we do have it. So it's 10 microcoulomb multiplied by omega, which is 52.7. 0.7 radians per second multiplied by 10 microcoulomb. So it will be 527 microampere. Maybe we can change it to half of milliampere, because micro will stay, but you have almost 500 here, yeah? So then we can write the current. And remember, my current is defined as a negative dq over dt, not positive. So it's a little bit change. Half of milliamp, and then sine omega t. Voila. How do you like it? Of course, we can find kinetic energy, I mean energy inside inductor as a function of time. I just have to make it square the current multiplied by inductance and over 2. I also can find the potential energy as a function of time, or energy inside the capacitor, charge square over 2c. And in principle, if I add them together, kinetic plus potential, the time dependent should go away. And we will get the total energy of the circuit. I would not call this mechanical energy. It's energy of LC circuit, yes. It's energy of the electric and magnetic fields. It's not mechanical energy. By the way, one way you can use these LC circuits, if you can excite such kind of oscillation. You have electric field changing in time, yes? Here. Because you have charge changing in time. So, and then you have also certain frequency at which you change this. The frequency was not large. Yes, what was the frequency? 8.4, yeah. So then, once you have electric field changing in time, it will start to produce magnetic field of the same frequency. And it will start to produce electric field of the same frequency. So basically you start to create, you produce electromagnetic waves. Here. Well, the frequency is only 8 Hz. It's not like something serious, very low frequency. It's not even mega Hz, yeah. But so then it could be radio waves of very long wavelengths and very small frequency. We can solve an example. Let's say very simple, but rather practical than complicated. So, for example, I would like to have certain frequency. Let's say, especially for Lenin, we would like to have a frequency 430 megahertz. So I would like to have a source of radio waves. And this number 430 megahertz is not a random number, yes? So then what kind of inductance and capacitance I should have in my LC circuits to provide this? This is relatively large frequency. So let's say if capacitance would be 10 microfarads, what L should we pick? To have this frequency? Yeah, of course, this is very simple. It's very straightforward, but it's practical. It's more like real life example rather than practice example, because this would be already a radio wave. This is relatively high frequency. It's not visible light, of course, or microwave. Well, but so we have a resonator, and we would like to resonator to work at this frequency. So basically produce radio waves of given frequency. Let's do this. It's relatively fast. The frequency equals 1/2 pi square root of LC. And I'm looking for what? For the inductance, yeah? What would be the equation? 2 pi f square is 1 over LC. And I'm looking for the inductance. I don't know, you can double check if this is the correct formula. Let's change microfarads to picofarads. Otherwise, our inductance will be too small. The picofarads would be better. Picofarads is what? 10 to minus 12. And this pico and megahertz squared, they should cancel out each other. That would be a more reasonable value. So let's say I'm going to use 10 picofarads. And then what should be the inductance? Can you give me the number? So if I'm not mistaken, then the answer should be somewhere here.
Is it 13,699?
Is
Oh,
it supposed to be small?
What did you get it at?
I forgot one of the 10 times
12.
10 to the to the
Yeah.
6.
So these are picofarads, yeah.
Oh yeah, so it's
It's a 1, 2, 3.
1.3.
So we're talking about micro
10 to the minus 8.
10 to negative 8, yeah? Henry, what is this you say?
1.3. Or did you
Hmm.
get something else, Derwa?
No, I don't know. I didn't get anything.
No, I forgot to square. I'm going to check right now.
It's 1, 2, 3.
I also got that, but I don't know.
Close to this, yeah? 1.3,
Yeah, 1.36.
6, yeah? So we can say nano, Henry, if you want to make it 10 to negative 9. So this combination of these two values, 10 picofarads and 13.6 nano Henry, should give me this type of frequency. Does it make sense? And usually you use this type of LC circuits in radio receivers. So if you want to tune to, I don't know what your favorite radio station, like 100 megahertz, and then you can have a resonance of your LC circuit with the external signal. This would be interesting maybe to mention. What if I put resistance, and we can move on after this. So this resistance would be on a conceptual level. So LC plus R without serious calculations. So all the same. Capacitance. Now I'm going to put resistance and inductance. Charge, current, resistance, inductance. What would be the loop rule for this? Well, we already wrote this loop rule before, yeah? So let's go clockwise. So it would be Q over C minus current multiplied by resistance, and then minus inductance di over dt, and also the same ratio, relation between current and the charge. So the only difference is now I have extra term, and this extra term will represent me the drop of potential across the resistor. Again, I want to do this at conceptual level without really solving any numerical examples. So if I plug my current here and I use negative sign, so it will change it to positive, then wait a second, is it all correct? Q over C, negative I over R, negative. Is the something is going? Oh no, it's all correct, yeah. So then the L second derivative is Q over time will be equal minus 1 over CQ minus resistance dq over dt. This would be the equation, and of course it's the same equation as before, plus we have this new term, current multiplied by resistance. Okay, I want to remind you equation for simple harmonic motion when you have friction force. The mass times acceleration would be equal negative kx, negative some coefficient beta or b and v. And this velocity is dx over dt. If you remember, we call this damped simple harmonic motion. And again, resistance is gonna play the role of friction here. That means because of this friction, the simple harmonic oscillations will die with time. And I know the solution for this guy, yeah, for this equation. I don't know if you remember this or not, but the solution was some initial amplitude exponent minus gamma t multiplied by cos, if I remember this correct, so it's going to be harmonic oscillations, and omega was a square root from omega naught square minus gamma square, something like this. And the coefficient gamma was was it beta over 2m or something like this? I may not remember this correct, so, but what I'm trying to say is that I know the solution for this damped simple harmonic motion is pretty well. And I know that the amplitude of oscillations will decrease exponentially. And this is how I calculate the coefficient of this. So then we can interpolate this to LC plus resistance circuit. We can say that my charge as a function of time, when it oscillates, Q, starting from initial value, will gradually decrease because part of the energy will go to resistance and disappear into heat. This is what we call under-damped simple harmonic motion. So my charge, the amplitude, will go down like this, and the parameter gamma, beta over 2m, remember beta over 2m, resistance over 2m. And instead of m, I put inductance. This is the same time constant for as we use for RL circuits. 1 over 2 tau. L over R, that was the time constant. So then the typical time of decaying would be double tau. So then normally RL circuits, you just have a decay. Now you also have oscillation on top of the decaying exponents. This is nice. That again, it's a full agreement between these two, like a simple harmonic motion and RLC, the analogy. It's very nice. I don't remember if it's really bit over 2m. Something like this I remember, yeah? It should be like this. And capacitance doesn't matter, yeah? K constant. Yeah. We can have resonance, so we can have external force of certain frequency, and if certain external force is harmonic, then it could be a possibility for resonance in this case. This is what radio receivers they use. They can tune to very certain frequency for which you have resonance, and this would be the frequency you receive the radio station. If you want to listen to another radio station, you just tune to another resonant frequency. In this case, external signal you treat as external force of certain frequency. I would say it's nice. It's good. Maybe we have time for a more complicated example. Maybe not. Let's try. At least we can start. Let's spend on this 5 minutes. I'm gonna do something non-trivial. At least I'm gonna start working on this. So let's say you have a capacitor C, and then maybe C1 with some initial charge or voltage initial, okay, charge, Q0. Then you have switch, and you have another capacitor, C2, and the initial charge is 0. So you don't have any charge here. And they connect it with an inductance. So then the initial distribution at time equals 0, that Q1 equal Q0, Q2 equals 0, and of course there is no current because the switch is open. And then I would like to close the switch. So then what will be Q1 as a function of time? What will be Q2 as a function of time? And what will be the current as a function of time? This is non-trivial because you can just take a numbers and plug these numbers into an equation, because There is no equation for this system. We will have to derive this equation, but we can assume that probably C1 and C2, these are just two capacitors which connected somehow, maybe in series, yeah. Then the charge will be oscillating. So the charge will go one way, another way. So inductance connected to the both capacitors will create this as a simple harmonic motion type of circuit. But how would you find Q1 as a function of time, Q2 as a function of time? Maybe we can write a couple of equations or laws which can describe me this. That would be an interesting question. I would maybe treat it as a good extra credit question, but I don't want to. I just want to say that we don't have time for this, unfortunately. But let's try to write down equations at least. And only what we can write is the loop rule. The loop rule. Let's introduce the currents Q1 and Q2, and the charge conservation law and the energy conservation law. So energy conservation law is the loop rule. Plus we have the charge conservation. That means if you have some charge left from capacitor C1, the same amount should come to capacitor C2. Look at these two plates. They are not connected to anything, yeah? That the total charge on these two plates should stay the same, no matter what. The total charge, yeah? So if Q1 will reduce, then Q2 should increase by the same amount. And the same goes for these two plates. Okay, how would you write a loop rule? Let's say the charge will start to leak, and we have a circuit like this. Q1, current, Q2, inductance. So the loop.
Would it be
Q1,
QC minus, yeah,
Q1 over time, of course, the function of LC. This is drop of potential. Then
minus Q2 C
C1. And
minus,
then minus, yeah. Let's put equal L di over dt. So one equation, then probably Q1 as a function of time plus Q2 as a function of time should be always be the same, and it should be equal to the initial value. And then we need the connection between the current and Q1 and Q2. So maybe we can say that the current will be equal. If I think about Q1, Q1 is decreasing, then you have positive current. Like this, yeah? Or positive dQ2 over dt. This should be enough actually to solve this. Apparently, if you can find Q1 as a function of time, you can easily find Q2 and current. That's not a big deal. So just if you can find only one of them, that would be enough. That would be cool. So this is a little bit less trivial system than just LC. Because if you just have LC, then you just write the answer. But for this one, you have to write equation first and then solve it. That would be non-trivial. Okay, let me summarize. We're basically done with non-trivial examples for inductance. So we consider it inductance connected to resistance. We call this RL circuits and some external battery if. So then we have charging process, we have discharging process. And that was pretty much straightforward because it was simple, similar to RC. When you have LC circuits, this is something new. It can be related to simple harmonic motion with some substitutions like this. Even I can have a friction force and I have external force. The analogy will stay. That was interesting. And this couple of slides, it was just a reminding what was the solution for simple harmonic motion. And then we had this one example, another example. This is just a conceptual consideration that you have a friction and you have this damped simple harmonic motion. Example D would be a good example if you want to practice and solve this. And I have like 10, 11, maybe 15 minutes. I want to start talking about something else. But we are done with inductance as a separate topic. I plan to start to talk about AC power supplies when you have alternative current. And then we will start plug to AC power source, resistance, capacitance, inductance, and combination of resistance, capacitance, and inductance. We're going to call this RLC circuits. This is the last topic for circuits. After we're done with RLC, we can start talk about electromagnetic waves and optics, depending how much time we have left. So let's use 10-15 minutes to talk about AC power lines or power supplies. It's number 3 maybe, yeah? Because we were talking about RL and then LC, now it's just AC. So when we say AC, which means alternative current, this is how we can label this. So the voltage provided by the source would be a function of time. Cos or sine, it doesn't matter because it can be shifted. So for me, let me pick cos omega t. And then we assume that if we need to introduce a shift, then yes, I'm going to introduce a phase shift if I want. So this type of signal will give me a V as a function of time. So basically it's a cos function, which has period and frequency. So V naught is called peak value. Peak or maximum value. Or amplitude, yeah. So when you have a signal like this, basically it's a simple harmonic motion. So the signal oscillates from negative peak value to maximum peak value. And this should remind you generators. If you rotate a generator at constant speed, you basically provide a signal of this type. And even we introduced before the formula for the peak value. It was 2 pi f NBA, number of turns, magnetic field in this generator and the area of the coil. So now we just say that we are given a source of this type and that's it. Then F is the frequency. So then we can introduce period and omega if you want. So for example, we can have let's say 120 volt at 60 Hertz. So this would be a power supply. It's a standard US power outlet, which provides you roughly 120 volt and 60 Hertz. But then the question could be, this 120 volt, is it a peak value or it's some kind of average value? What would be your guess? This 120
Average.
average. And you're absolutely right with some comment because, and I would like to comment on this average value. It's not a peak value, by the way, yeah? So we have to talk about some average value because, so let's say your signal look like this. So it's going to be a small value and then very large okay, like this, yeah. I did this. So if you signal of this type, then for most of the time, the signal is low. If you just give me the peak value, the maximum value, you're gonna confuse me a little bit with the peak value. Of course, it may be important to know what is the peak value, but peak value does not tell me exactly a lot about the signal. So then, instead of peak value, we would like to use what's called average. Average. But the problem with the average well, let's define this. So the average value would be an integral from the signal over time. And then if a signal repeats itself, you can say from 0 to period, 1 over period. If the signal doesn't repeat itself, you can define it like this. So you just select some time. And then you make a limit when time goes to infinity. But we work with the signal which repeats itself, so it has period. So that could be enough for me to use the definition like this. The problem is that the average value for my signal would be 0. So this is a period, yeah? So you have positive area and you have negative area. In this case, what is the average value? The average value is 0. So unfortunately for us, we can't use average value to characterize the signal. So then people start to think about it and then say, okay, peak value may be not very convenient. Average value in this particular case is even less convenient. Then people introduce something else. It's called RMS. And this RMS value stands for root mean square. So this V RMS is defined like this. you take average from signal squared. Because you make it square, then it's going to be always positive. Then the average value from this square, v square, is not going to be 0. But once you calculate the average, then you can take square root to get again some voltage. Because if you don't make a square root, it's going to be voltage square. And this RMS stands for root mean square. So you have mean value and square root. Root mean square, yes, RMS value. It's basically what you see is how you make this abbreviation for RMS. And maybe we can calculate this RMS value for a harmonic signal right now, and we can relate the RMS value and the peak value, and see if you have this 120 over 60 Hz signal, then 120 is RMS. And in most cases, you're given RMS values. You practically never know the peak value of your signal, but you can calculate this. Okay, let's calculate it. It's not a big deal, yeah? So let's find this. Find VRMS for V as a function of time equals V naught, cos or sine, doesn't matter. I'm gonna use omega, but we can use 2 pi f or omega. So then V square would be V naught square square omega t. So then the average from V square would be an integral from 0 to period from V square.
What is the difference between RMS and absolute deviation?
The standard deviation, if you have non-zero average, then they will be different. But if your average is 0, then there is no difference. If you remember, the standard deviation can be found like this: average V square minus average V square. Yeah. And then if the average V is 0, then they're the same. So you're right. So this RMS basically your standard deviation. That means on average how far is your signal from its average value from 0. So then there's kind of the width. So I'm calculating the average right now from the signal square. Cos square, there was a function, there was a formula for cos square. Is it 1 plus cos of double angle?
Isn't
2?
it? Oh yeah, over.
Yeah. Then when I plug it here, the integration from 1 over 2 will give me just period over 2. I don't know if I'm too fast or not. So this 1/2 instead of cos square, I just integrated from 0 to the period. So I'm gonna get period over 2 plus the integration from cos double omega t. What is antiderivatives from this cos double omega t? Sine, yes. Maybe double omega and this extra factor 2. but sign function is 0 at the beginning and at any integer periods. It's going to be 0 even if you have half periods. So then the average from cos double omega t is 0. And the average from this 1/2 is 1/2, basically. So the conclusion that the average from v square would be the peak value square over 2. Or if I take square root from this, then I can get v naught over square root of 2. This is nice. So I can relate for this particular shape of the signal. I can relate the peak value and the RMS value. So the coefficient which relates them would be the square root of 2. So this is true for any harmonic signals. Any cos or sine function, so any harmonic signal. And this is very nice. Now, usually you are given RMS value. And people don't call this RMS or average. By the way, instead of RMS, people call this average. Even average is 0, you still call this average because average probably easy to say and understand rather than RMS. So the RMS is not very popular term. Even technically, you can speak about average value. Average value is 0. You speak about RMS, but you call this average, which is strange and could be confusing. It could be even more confusing. You never call this average or RMS, you just call this voltage. You can say that my power outlet gives me 120 volt, and you don't say that this is RMS or average. So then you never talk about peak values unless there is a separate statement that this is a peak value. You always assume that you are working with RMS or average value. And when you say 120 over 60 is my power supply, then this 120 volt is actually the RMS value. It's a kind of a small agreement. So 120 volt over 60 hertz power supply means that my VRMS is 120 volt and the frequency is 60 hertz. So what would be the peak value? VRMS, of course, should be less than the peak value by square root of 2. So the peak value will be greater than RMS value by the same factor, yeah, by square root of 2. So for this power source, the peak value would be square root of 2 multiplied by 120 volts. And you can help me then to calculate it. So square root of 2 is close to 1.4. So it's 120 and then 48. 120 and 48, 168. So
169.7.
169.7 volts. So then when you plug something into your power outlet, then you should understand that the voltage is oscillating between negative 170 volt and positive 170 volts, yeah? It's not 120. It's 120 only on average. And technically, it's not even average, it's RMS. So it's a standard deviation from the zero. On average, it's still zero. The standard deviation is 120, and the peak value is close to 170. So if it's crucial for you that the voltage shouldn't exceed certain value, then you should think about peak value. Because what you're given is 120, and this is your average. Okay, maybe it's good for today. For me, it was important to just introduce RMS value. And next time we will be more serious about these AC power sources. We will try to plug the different elements in this AC power supply. So for example, like this, we can plug resistance or inductance or capacitance or combination of them. So, and the goal would be to find the current. And the question is, can I use Ohm's law? Because you have power supply, you have resistance. Can you find current normally as you would like to do? Well, sometimes yes, sometimes not. It depends what is your load. Apparently, if this is inductance and capacitance, it's getting more complicated. Okay, thank you. Maybe questions?
Thank you, Professor. We'll see you the week after, right?